Hello again. So today we're still on the recursion example, but this time we're moving from the analytical work to the code. And what we're going to do with you is to code up the recursion relationship that we've been dealing with that takes step n from steps n minus 1 and n minus 2. And if you run it in code, of course the round off error will be there, and that will breed and cause problems with stability. So let's move over to the MATLAB now. Okay, so last time we were looking at this numerical example of numerical instability, recursive example, and we had this recursion relationship, which was, let me write it down here on my MATLAB window, which is 3 of x of n equals 10 of x n minus 1 minus 3 of x n minus 2. Okay, so that was a recursion relationship. The new value was 3 times that. Now, and we showed that if you just had a purely analytical solution with the right initial conditions, you just had a decaying solution. But if you add in a little epsilon of random error, such that always exists on computers, then you always will get, that will then project onto exponential growth. So remember, let's remind ourselves, we're looking at the MATLAB window now. Our epsilon, as our round off error, is 2.2 times 10 to the 6. So what I want to do is just key in MATLAB the code that's in the lecture notes that applies this recursion relationship. So I'll just move that bit of code out of the way. So I'm going to start off with format long. This is a very useful thing to make the so this makes the increases the number of decimal points, number of increases accuracy, if you like, of output. So I'm going to put some comments in here, not normally usually when to do that. And then we're going to, so what we're going to do is we're going to go back to my, and we're going to label each of these things in code. So we're going to call, I'm going to call that, we're going to call x of n c in our code. We'll call x of n minus 1 b, and then we're going to call x of n minus 2 a. Okay, just for convenience. Okay, I could call them xn minus 2 if you want to be absolutely explicit, but it's quite common to do shorthand in code. So I want to then first put in my initial conditions. So I'm going to have a is 1. Remember, the initial conditions were that x0 was a third. Sorry, x0 was 1, and x1 is a third. So that corresponds to x0 equals 1, x1 equals a third, and they're your initial conditions. Okay, so that's all well and good. So if we had no pollution, if you like, by random errors with this solution, or we had a stable method, this would behave well. But we reckoned from our analysis previously that actually when we perturb these values by the random error, they're going to project somewhat onto the growing mode as well as decaying mode. Now I've got the semicolon there, so it's just pushed out B. So that's both a strength and weakness of MATLAB is it tends to output everything unless you put a semicolon afterwards, which you've probably come across before. That's a sort of so the n is a counter. we're going to use to counter the loop. So then we're going to do while, so we're going to start at n is 2. Reason being is that we've already set the values of 0 and 1 in the initial conditions. So then we're going to do a while loop in this case. So while n is less than 40, so we run for less than 40 steps, and then we're going to, so then when you do this, you know, often you do this in a script, but you can do it at the command line. When you do this, then it just recognizes that you set up some sort of loop, and then waits for the contents of the loop before you've ended the loop. So within the loop, then we're going to do our recursion relationship. So so what I'm going to do with this relationship is divide through by 3, right, to give me an expression for x of n. So that coefficient becomes 10/3, that coefficient becomes 1. Yeah. So C equals 10 times B minus 3 times A, all divided by 3. Okay. So I could simplify this a little bit by putting that as 10/3 if you want. Let's do that. It doesn't really matter. And that. Okay. So that's our recursion relationship. Formula. And what I'm going to do is just display some things as we go through the loop. So what I'm going to do is display the following things. So I'll put them in a little in this way. I'm going to display the step. I'm going to display C, which is our solution, numerical solution, and then 3 to the minus n, which is our true solution. So we display step, the new numerical solution, C, and the true solution, which is 3 to the minus m. The true solution is, remember, is the one that if you use these values without any, the analytical solution without any perturbation, but we reckon there's this epsilon lurking under there that's going to be adding on or taken away, it doesn't matter, to these initial conditions, and it's going to corrupt it. Okay. So we've done this common trick where we replace a thing that applies every step with just a single value, C, B, and A, just for simplicity. But if we do that, which is quite common, we need to shift the values of C and B for the next step. So for the next step, we need to make sure that the xn-2, the new x-2 is the previous xn-1, right? So A equals B. And B, then also the xn- for the new xn-1 is the old xn, so B is C. So this is shifting values of xn-2, xn-1, for new step, and then it goes for the new step and it repeats. If you don't have this shifting thing in there when you make this sort of substitution, then the method will just get stuck on the first step. So it's really important to identify, and you'll see this come up in a few times in the codes we'll look at this year. And finally, we want to increase, we're using n as our counter, so we increase step value So that's the end of our contents of the loop, and you notice that the MATLAB suppresses the command line, which is these two arrows, whilst you fill in the content. So we've got a recursion formula, we've got some displaying, we've got shifting for next value and increasing step value. So once we've done that, we can close off the loop and it will run. And it gives us all these data. So let's just have a look early on. Okay, so it's not particularly well formatted, it doesn't matter, but we've got n, we have these three numbers here. We have n, C, our numerical solution, and our analytical solution. So in the early stages, when n is 3, we find that the numerical solution and the other one are very close. Let me just try and, I know. Okay, so I'm going to try and just do a bit of scribbling on top of this code at the minute, just to so this first number is our numerical. That's our step. Step 3, that's our numerical solution. And this is our analytic one. Okay. And they're very close in the early stages, so that's all well and good. Okay. But the punchline for this experiment, this is like a numerical experiment we're doing, comes further down. That's in the early stages. So let me just remove all that stuff. And let's see what happens. And this is why I use the format long, the increased accuracy, so you can see the numbers. So if we now go to n is 27, say, just picking it fairly randomly. So, oh. Yeah, let's go to n is 27 where we can actually see some of the solution. So n is 27 here. There is a big difference now between the numerical and the analytic. So the analytic solution is decaying quite nicely. There's n tends to infinity, but numeric one is actually increasing again. And the reason being is because of this epsilon 3 to the power n term, okay, that we've got. It's kind of something like this. Epsilon 3 to the n is causing growth of the numerical solution that it doesn't in the numerical analytic solution. So this is why this is a really nice example, because I've just blindly applied this recursion relationship, but because it's got this parasitic mode within it, I just do a very tiny adjustment to the initial conditions. One that I haven't done explicitly, is just there because you have this round off error, then you suddenly get this big disparity between the numerical and analytic solution. So this recursion relation then is a poor numerical method for solving this problem because it's numerically unstable. Yeah. So let's just finally round that off by going right to the end. Now, in the accuracy we're using here at stage 39, say, it's gone pretty much to 0 with the accuracy we're doing, but the actual analytic solution is growing So let's just confirm that. And it's the parasitic mode. So that's bad news. So this is probably an example in this module where you should go away and experiment and try and understand it. Come back to me with any questions in small group sessions. Because you know, sort of getting your head around that this analytic solution works on paper, but it doesn't on the computer. It's all because the round-off error. Maybe it's a bit of a conceptual change you need to get used to. It may be obvious if, to you all, but it's not. So this really shows this round-off error issue, this fact that we've got limited storage in the computer is really important, and really why we need numerically stable methods as we go forward. Okay, so I think that's quite a good place to stop, and I'm going to pick it up again with numerical methods for time stepping, which is what we started with briefly, and we're going to start with forward Euler, which should be a familiar friend from last year, and leapfrog, and we're going to move through the whole in several videos, lectures. We're going to move our way through all the methods and analyze, and as we go through it, we're going to analyze these two things, the accuracy and the stability. So even if you've encountered these methods before last year, you should at least sort of your level 2 understanding, if you like, of this material should be that you're able to explain and give reasons why it's a certain accuracy, this method, and it has a certain stability for certain situations. Okay, so that's really where we're going for the remainder of this section of the module. And okay, I will see you then.